Let's review a few of the things that we talked about in our first online class. I want to start with the definition of electric potential difference. So remember, delta U is the thing that you're familiar with from Physics 1. It's the change in potential energy. And just like a mass has potential energy in a gravitational field, a charge has potential energy in an electric field. What we do, though, here is we define a new thing called electric potential difference as the change in potential energy per charge. And so the idea here is that even if we don't know how much charge is moving in an electric field, what we can know is what the electric potential difference between 2 points in the field is. And it turns out that electric potential difference is usually, it's the thing that we actually know in electricity or in circuits problems. You'll notice here that this formula defines the volt. So a volt is a joule per coulomb. Okay, so V is J over C. As I just mentioned, the electric potential difference is related to the underlying electric field. And if the field is not constant, then it's related by that integral. If the field is constant, then the electric potential difference from one point to another would just be E dot delta R, or E delta R cosine theta, okay, as always for a dot product. When we're doing problems involving charges moving in electric fields, when we use an energy approach, instead of talking about the electric field, we talk about the electric potential difference. And usually, again, what we know in the problem is delta V. So oftentimes, as in the two problems we did right before the end of last class, we take our definition and we rearrange it. So in other words, what we need to be able to plug into the work energy theorem is delta U if we want to find what's going on with the velocity. And so delta U is equal to Q times delta V. By the way, the AB notation, again, just is explicitly reminding you that we're going from point A to point B in the electric field. All right, let's take a look at a problem that looks at this idea. So two parallel plates are connected to a voltage of 120 volts and are separated by 0.1 meters. What is the magnitude and the direction of the electric field between the plates? So here what we're trying to figure out is what is the relationship between the electric field and the electric potential difference. So first of all, remember what we talked about last time, where we said that the positive plate is always at the higher potential. So we would say the right-hand plate is at 120 volts and the left-hand plate is at 0 volts. And remember that the electric field, since we know always goes from plus towards minus, you'll notice that the electric field is always in the direction of decreasing electric potential. Okay? And that's in fact the significance of that minus sign. And I'll say that a few more times over the course of today. All right, so in this case, because the electric field is constant between the plates, I can instead use the non-integral version. So delta VAB is negative E delta R cosine theta. And I'm going to integrate from the 0 voltage plate to the 120 voltage plate. So that's delta R. And so what you'll notice is that if I go from 0 volts to 120 volts, the angle between E and delta R is going to be 180 degrees. So delta VAB is equal to minus E delta R cosine of 180. And so you'll notice that's just going to get rid of the minus sign in the front. And I get that delta VAB is equal to E delta R. Okay? Or finally, the electric field is equal to delta VAB, the electric potential difference, divided by delta R. Now, we can finish the problem here. We've got the change in voltage from 0 to 120 would be 120 volts. And the distance between the plates that we're going is 0.1 meters. And so we would get 1200 volts per meter. Now, a couple important things here. Again, first of all, what we've just done is we've looked at the relationship between the electric field between two charged plates and the electric potential difference across them. So that you'll notice that if I know the voltage across the plates and the distance between the plates, I now know how to calculate the electric field in that region. So that's an important connection. The other thing, though, you'll notice is that we got a different unit for the electric field than we've had in the past. So let's talk about that and see what we can learn from that. So in the past, in every chapter up to this one, we've said that the units of electric field are newtons per coulomb. Well, now all of a sudden, we've said that it's volts per meter. So let's first of all just make sure they're equivalent. We know that a volt is a joule per coulomb. So we've got joules per coulombs over meters. But we know a joule, thinking of the work formula, a joule is a newton times a meter. So we've got newton meters divided by coulombs divided by meters. And you'll notice that that gets us to newtons per coulomb. So a volt per meter is completely identical to a newton per coulomb. So that's good. Obviously, we want our units to make sense. But this new unit for electric field, volts per meter, I want to show you that it gives us some insight into what is the relationship between electric potential difference and electric field. So let me just draw some equipotentials. Remember from the lab what an equipotential is. We'll talk about it more in today's class. But an equipotential just means a point in space over which the potential is constant. So these aren't these aren't surfaces or anything. I'm just drawing lines and saying, let's say that everywhere here, anywhere on that line, the voltage is 20 volts. Everywhere on this line, it's 30 volts, 40, 50, and 60. Okay, so I'm just drawing equipotentials in a region of space. Well, one of the things that you learned in the lab was that electric field lines, equipotentials, that electric field lines are parallel to electric potentials. So in other words, if we were going to draw the field lines in this picture, we would draw them this way. And the electric field lines, remember, go in the direction of decreasing electric potential. But notice, if I now asked you, what is the electric field in this region of space? If you just understand the unit, you'll notice how easy it is to figure out. What electric field is all about is simply how is the electric potential changing per distance, voltage per meter. So if I told you that these lines were separated by a distance of 1 meter each, then what you would notice is that the electric field is changing by 10 volts per meter. Okay? So the electric field in that region of space would be 10 volts per meter to the left. All right, the next thing we want to look at is the following problem. We want to look at what is the electric potential difference moving from point A to point B near a point charge Q. The first thing that I want to say about this is very similar to what we did back when we did problems with gravity, but instead of using potential energy, we're looking at electric potential difference. So I'm not saying that I'm moving a charge from here to here. I'm just saying for anything, what is the difference in the electric potential from point A to point B? Okay, so we're trying to figure out delta V directly. We'll see that once we understand that, it's going to be useful to solve problems where we actually now put a charge at A and let it go to point B. So we start out with our definition of electric potential difference in terms of the electric field. And we know the electric field of a point charge. Remember, the electric field is K Q over R squared. So what I want to do is I want to just plug that in for E and do the integral. Now, we're going from A to B. Notice that the electric field is to the right. But also, since we're going from A to B, notice that dr is also to the right. So when I rewrite this integral, the first thing I'm going to do is just recognize that it's a dot product, so that I can write that as E dr cosine theta, get rid of the vector signs. And then we can see that theta is equal to 0, the angle between dr and E, and therefore cosine theta is equal to 1. So now I'm going to put in, I've got negative the integral from RA to RB of K Q over R squared dr. Okay, so I've gotten rid of the cosine since it's equal to 1, and I've put in what E is. The next thing I'm going to do is take anything that's a constant out of the integral. So K is a constant, and the charge that's creating this electric field Q is a constant. So K and Q can come out. And I have the integral from RA to RB of dr over R squared. Okay, at this point, since you guys are either in Calc 2 or have already taken Calc 2, you could go ahead and solve that for me. Guys got it solved? All right, well, so first of all, remember that the integral of dr over R squared, or the antiderivative, I should say, is just minus 1 over R plus C. And of course, since here we're doing a definite integral, we don't really have to worry about the constant. So let me go ahead and evaluate this now based on that antiderivative. So delta VAB is equal to minus KQ, and now we're evaluating minus 1 over R from RA to RB. And before I do that, actually, let me just make it simple on myself and get rid of the minus sign. So we have KQ 1 over R, and we're evaluating that from RA to RB. And so what we end up with is delta VAB, the electric potential difference between those 2 points in space, point A and point B, is KQ times 1 over RB minus 1 over RA. Okay, so that's our result, and it turns out that we can simplify this result in a certain way, and that's what we'll talk about on the next slide. Remember that back when we did potential energy problems with gravity, we said you could always set the origin wherever you wanted to be. You know, if you were thinking about a mass sitting on a table, you could say the potential energy there was 0 by setting your origin at the table. Or you could have said that your origin was at the floor, and then an object up here on the table has potential energy. So you can always set where the 0 is, and that's because fundamentally in the work energy theorem, remember that it's always delta U. So where the origin is doesn't matter, because once you subtract two different potentials, the origin cancels out. Well, the same thing is true here, because remember, electric potential difference is related to potential energy. So what we do is we arbitrarily say, let's set the zero of potential to be at infinity. Here's what we have so far. We have delta VAB is equal to KQ times 1 over RB minus 1 over RA. But now what we're going to do is we're going to say, let's say that point A is all the way out here at infinity. And we're just going to arbitrarily say that the voltage, electric potential, at infinity is 0. So to write that out, remember delta VAB stands for VB minus VA. That's equal to KQ 1 over RB minus 1 over RA. But we're saying, by definition, that the electric potential at infinity is 0. Well, of course, 1 over infinity is 0 anyway, and we just get that VB is equal to KQ over RB. And we now just drop the letter and say that the electric potential of a point charge is given by KQ over R. Okay, so the potential at distance R from a point charge is KQ over R. Notice now we're not saying potential difference, we're saying the potential. So the electric potential at a point in space R away from this charge is KQ over R. Notice that again, electric potential is really related to the underlying electric field. So if there's an electric field in a region of space, then there is an electric potential in that region of space as well. Now, for some of you where you've done work with circuits, you're used to the idea of there being a voltage in a circuit, but you can have a voltage in a vacuum or in air as well. Okay, so if we are a certain distance away from this point charge, there is an electric potential at every point in space in the same way that there's an electric field at every point in space. By the way, this formula also works for a sphere of charge as long as you're outside the sphere, because we know if you're outside a sphere of charge, the electric field is the same as the electric field of a point charge. Remember that electric potential is a scalar, but being a scalar doesn't mean it can't be positive or negative. So when you are at some distance from a positive charge, then the potential is obviously going to be positive because Q is positive. However, if you're some distance away from a negative charge, the electric potential in that region of space is going to be negative because Q is negative. And here you just see a graph of what that would look like as you move away either from a positive charge or from a negative charge. So at this point, I've tried to show you, where this concept of electric potential difference and electric potential comes from. At this point, we want to see how do we actually use this in a problem. So this would be a very typical exam 3 problem. So the problem says, and in fact, you'll notice from the formatting, this was a problem I gave as an exam problem in the past. So let's go through it together. What is the electric potential 1.5 meters from the center of an object with a charge of 4.5 microcoulombs? So we've got our charge here, charge Q, and it's got a charge of 4.5 microcoulombs. And we're asked to figure out what is the potential at this point. I'm just going to call that point A. And we want to know what is VA. Well, the good news is that's just an easy calculation. It's just a plug and chug. We know that electric potential created by a charge either a point charge or a sphere of charge when we're outside the sphere, is equal to kq over r. And here I'm going to put on an a because we're looking at point A. So k is our constant we're familiar with, 9 times 10 to the ninth. Q is 4.5 times 10 to the negative 6th coulombs. And divide that by a distance of 1.5 meters. And if you calculate that, you're going to find that the electric potential difference at point A is 27,000 volts. All right, let's keep going. B, what is the electric potential at infinity due to the charge? So here's point B, and point B is out at infinity. Well, we don't have to do any calculation for that because the electric potential difference at infinity is 0 by definition. Right? That's where we defined the electric potential to be 0. Question C. If a proton is initially placed at 1.5 meters from the object, what will be its change in electric potential if it moves very, very far away from the charge? In other words, to infinity. So the key thing here is pay attention to the vocabulary. I'm not talking about energy. I'm talking about electric potential. Change in electric potential. What is that? That's delta V, the electric potential difference. So the electric potential difference in going from point A to point B is just the potential at B minus the potential at A. So that's going to be 0 minus 27,000 or negative 27,000 volts. So that is the electric potential difference that the charge are between those 2 points in space. Notice, by the way, I haven't done anything with the fact that it's a proton that's going to go through that change. So here's the key thing about electric potential difference. It would be true for any charge that goes from point A to point B. Now, the next part of the question, we're going to actually use the fact that it's a proton that's going to move from point A to point B. So the next part of the question is, what is the change in potential energy as our proton now goes from point A all the way out here to B, which is out at infinity? So now this is where we're going to calculate delta U. So remember, by definition, delta V is equal to delta U over Q. So make sure you have the understanding of what's potential difference, what's change in potential energy. So we want the change in potential energy. So that's delta U is equal to Q times delta V. Okay? And if we want to stick the AB on there, we can. So now I care about what charge is actually moving from A to B. And in this case, it's a proton. So I've got 1.6 times 10 to the negative 19th. And I've got my voltage difference of negative 27,000 volts. And what I get is that delta U is equal to negative 4.3 times 10 to the negative 15th joules. Now, ultimately, what I want to know in this problem is how fast would our proton be going as it gets very, very far away from our 4.5 microcoulomb charge. Well, now is when I'm just going to use conservation of energy. So delta K plus delta U is equal to 0. Again, we're assuming there are no non-conservative forces present, no friction, no applied forces. So the change in kinetic energy will be 1/2 mv squared minus 1/2 mv naught squared. Notice that in this particular problem, the proton starts from rest, but in another problem it wouldn't necessarily. So just be aware of that. So that's 0. and that's equal to minus delta U. So I've moved delta U to the other side, and you'll notice this kind of looks familiar to the problem we did earlier of the charge moving in a constant electric field. And so V is going to be the square root of -2 times delta U over the mass of our proton. And if you plug in the numbers, you should get 2.3 times 10 to the 6th meters per second. Now, I want to just talk a little bit about this problem. Make sure you appreciate what we've learned. In other words, we now have an energy way to figure out this problem. Because we've figured out electric potential and electric potential difference, notice we could do this problem without doing an integral. If we were still using the forces approach, we'd have to figure out the work done by the electrical force here, and we'd have to do that integral every time we did a problem. But with the energy approach, we don't have to do an integral to solve this problem. All right, I want to talk a little bit more about equipotential surfaces. So again, this is something that you guys saw in the lab. Because we were doing a two-dimensional version of it, we had equipotential lines. But try to think of these diagrams three-dimensionally. So in other words, these circles here would represent spheres that are places where the potential is the same that is being created by a point charge. And that makes sense because if we're the same distance from the charge, then the electric potential should be the same. So around an individual charge, the equipotentials would be spherical. If we look at now this electric dipole, so we've got a positive charge and a negative charge, you'll notice what the electric potentials look like. And again, as you saw in the lab, the equipotentials, I should say, and the electric field lines are always perpendicular to each other because the electric field is always in the direction of maximum decrease in electric potential. Here are the two diagrams that you actually did in the lab. And again, you'll notice that the direction of the electric field is always in the direction of maximum decrease in the electric potential. Okay, so in this case where our line here was at 12 volts and our circle was at 0 volts, the electric field lines were showing you in what way do I get the maximum change in potential in going from this point to this point. That's what those lines are showing you. By the way, oftentimes equipotentials are related to the lines on a topographical map. So if you know what a topographical map is, it's a map that shows you where the elevations are the same. So for example, a mountain on a topographical map might look something like this, where each of those lines represents a certain height. So in other words, here's what my mountain actually looks like. And you'll notice if I approach the mountain from this direction, it would be less steep because there's a longer distance between lines versus this way. Okay, and that's what I'm trying to show you with this diagram. So think of those lines on a topographical map like the equipotentials. And the electric field is showing you what is the maximum steep way to go from one point to another. All right, I think that's a good place to stop for today. Please do come on to our online office hours so you can ask questions about what we've done today.